and the title of this presentation is Seismic Strengthening of Existing Buildings with Cross-Laminated Timber Panels. So yes, we are trying to actually strengthen either concrete or steel or masonry with timber. Short overview, just the initial motivation why we started this, why we decided to actually use cross-lam. Few short properties of thermal insulation properties of combinations of cross-lam and aerogel. Then I shall show you the first seismic finite element models that we did that actually sort of motivated us to work further on the subject. We shall go through the system concept development that we did for the unreinforced masonry structures, and then I shall show you the actual experimental tests. So these are really the hot buns because they are literally fresh from the oven, because they finished just pretty much before I came to New Zealand. So, why to do it in the first place? I come from Slovenia. Slovenia is a rather earthquake-prone country. Unfortunately, we've had this little era of very bad construction as far as seismic is considered, because from 1942, so the end of the Second World War, until 1963, when the first actual seismic, if you could hardly call them codes, came out, we have some structures that are literally ticking time bombs. For example, this is the structure here. This is a 10-story unreinforced masonry building built in an area that can expect a magnitude, or has seen earthquakes of magnitude 6.2 and higher, and the expected intensity is actually 8 point on the European scale. So basically we have lots of structures that are earthquake prone, but in addition to that, pretty much all the buildings built before the 1970s, so before the first oil crisis, didn't have any insulation, any thermal insulation. So to sum it all up, we have in Slovenia a huge number of energy-consuming, seismically unsafe buildings, and we wanted to see if we could maybe try solving both problems at once. In addition to that, we wanted to see if we could do it actually in a system that's fast, that's simple, and it would also not take much space. Now there's a huge number of different systems for seismically strengthening existing structures on the market already, from carbon fibers to torquecrete, shotcrete, injecting additional steel frames and dampers of all sorts. But we wanted to do something like that, as prefab as possible. So if it would be possible that the whole panel would just come to terrain, use some basic craning, and then attach the whole thing onto the structure and basically have the structure both seismically strengthened and thermally insulated. So just a really short word on the thermal insulation. A few of our friends from the University of Ljubljana were fiddling around with the possibility of insulating cross-lam panels with aerogel, which is, if somebody doesn't know it, this is the basic material. It's also called the blue fog. The blue fog. Its more practical application is the space loft made by Aspen aerogels, and if you just look at the numbers, thermal conductivity, it's about 3 times more insulative as polystyrene. Unfortunately, it's more than 3 times expensive polystyrene, but however, if we look at the final, let's say, combinations of 10 centimeter cross-lam panels that are combined with various insulations, we can see that with a combination of this 10 centimeter cross-lam and the 6 centimeter layer of insulation, we're actually getting the same insulation value that we are by just having nearly insulation without the strengthening material. So technically, with a 16 centimeter layer, we thought that we could be on some good way to actually thermally insulate and seismically strengthen the structure. However, the seismic strengthening was still under big question. So we did our first model using the, if anybody was ever in Italy, there's this huge laboratory there in Ispra, and here is the place where this 3-story reinforced concrete frame building was tested. This is the so-called spear construction, and it represents a typical reinforced concrete frame that was built in the majority of the Mediterranean region during the, let's say, mid-20th century, before any, well, literally before any seismic codes were introduced in Europe. And so we were using SAP 2000, and this is what we did. We did a few variants. Once we tried to strengthen it with short cross-lam panels, and the other ones with long cross-lam panels. Now, this may this picture may seem slightly, do not let it guide you. This crossline was not installed as a infill, it was actually attached next to the structure. So this is sort of the proposed detail we were using. Why we're using BMF 105 brackets? Because those were the actual brackets that we have some proper experimental response for. Just to go to the results, the basic structure with itself could, according to displacement-based design in the N2 method, so based on the Eurocode 8, could withstand little less than 0.2 G. Now, Eurocode is very conservative when it comes to old structures, especially if you have smooth reinforcement and so on. You're ending up with very, very low resistances of structures. Nevertheless, if we try to strengthen the structure with short wall segments, we're ending up here. So this is a very slight increase. This is the pushover curve, the bilinear pushover curve. We're ending up with a very slight increase in strength, and we're actually ending up with just slight increase also in the base in the P ground acceleration. So technically, this structure could not withstand the earthquake in the most seismically endangered areas of Slovenia. However, if we're using longer panels, then we're not getting that much rotation from the panels. We're actually getting the stiffer structures. That's exactly what we want. We're actually getting way up higher in the inelastic spectra, and that's of course also resulting in a way higher allowed P ground acceleration. It's literally doubled. Now, of course, this was only a finite element model, and it was actually done on concrete. Now, we all know that concrete has quite some deformation capacity, even though if it's not made with under the newest codes. The bigger problem was, of course, masonry. Masonry is quite brittle and also has very low deformation capacity. So just to look at a few examples, this is actually from New Zealand, and all the pictures I'll be showing on this slide are actually, I've gotten from Jason Ningen, and I think a few of them might also be from Andy Buchanan, so thank you in this place. Now, there are several variants of actually strengthening masonry. We've also seen some cases with steel frames. This is another one which is done more properly because it actually has more bolts that attach it to the main structure, and we shall soon see why. The problem with earthquake is that, especially with earthquake in masonry, and trying to strengthen masonry, is the difference in stiffnesses. And of course, it's also the connections that matter. So you cannot just put one strengthening, rod or tie on every few meters. You have to make sure that you spread the load. Otherwise, you get very high local stresses, and that's what we were trying to avoid with our system. So we tried to smear the load transfer points to avoid the local stress concentrations. The next thing was to try to avoid out-of-plane failure on masonry. Now, this is again a case from Christchurch. The problem is that the masonry was not attached along the height of the light frame structure, because quite some years ago there were actually tests conducted at American universities that proved that if you actually attach masonry, so in this case it was also only facade masonry, to the light frame can actually take the load, out-of-plane load, caused by acceleration on the masonry. So this is also one thing that we had in mind when we were developing the system. This is probably the earliest sketch that we did. However, the concept stayed the same pretty much during the rest of the development. So if this is an example of a, let's say, typical connection in timber, typical steel timber connection, we have lots of pinching, slip and degradation and so on. This is something what we were technically aiming for. So a bit more, getting into the steel type of hysteresis, more full hysteresis, stiffer, stronger and so on. Now, this is sort of the first idea of the energy dissipating device, or where we could actually control our joint from. Steel is very, well, it's very, very good if you want to have some proper energy dissipation, and it's also easier to control. Now, that's why we wanted to pretty much over-design the connection between the steel and timber, and we also wanted to do that for the connection between steel and masonry. However, we had no clue on how that would behave, because literally until just recently you didn't have any data on how chemically injected bolts behave in masonry if you subject them to cyclic loading. So, you know, as we evolved along the way, the concept got clearer, so we saw that we have to make like a two-stage system, so with which we ease up the actual assembly of the system. So we have a steel tie going around the building, and then we were attaching our panels with some so-called steel shoes. The very narrow, you know, perforated steel that I showed you in the former picture changed to somewhat like this. And this is what actually we finished up with in the end, and what we have also actually tested. So you can see the steel plate. This is just a section that actually goes around the building, and it's actually bolted with chemically injected bolts into the masonry or concrete. Then you have two little bolts sticking out, I mean two for the case of one shoe, to which then this steel shoe is attached. And these little consoles, if you want to call them so, were supposed to use, we wanted to use sort of this dog bone effect on them. So we would try to use them as a control for our joint. And the steel shoe is then connected to the cross-lamp panel with on from the sides with self-tapping screws, and here you have two Siga Idefix elements. I shall show you later those elements on the pictures. I'm sure you've seen them already. So the experimental tests were then conducted at our National Institute. We were using just the standard type walls, masonry walls, so 1 meter wide, 1.5 meters high. And of course we started off with compression tests to actually get the first idea where our compression strength of walls were, and based on that we have then adjusted the vertical load. During the test we actually went for quite a high vertical load, actually 60% of the maximum, so we did not get any rocking in the shear walls, we just got pure shear, which we will also later see on the photo. So the first specimen we did was actually glued on to the masonry. We used epoxy-based glue made by Sika, and just a 4mm layer, because laboratory walls are actually built quite with quite a high precision. However, this glue also allows for up to 2 centimeter gap. So if I see 6 bolts here, these are not there to actually achieve some sort of a dowel effect. These are only here to slightly pre-stress the cross-lamp onto the masonry, so we don't get premature failure of timber, and sorry, of the connection, so the glue line, if you want. After the test, you see that the glue has actually worked. I mean, the rupture did not occur in timber, not in the glue, but actually occurred in masonry. So the masonry basically peeled off. This was the next one, so we tried bolting it. So before that, I was showing you these steel plates, as are they. Well, technically, they should be around the building, but as we're only working with small specimens. So through the little holes, they're bolted onto the masonry. You see some bolts sticking out. That's where the steel shoes come on. All the nuts were cone shaped, so we tried to avoid the slip as much as we could. And this is the actual shoe, which comes to the timber. So these are the Siga Idefix elements, which can take quite a lot of tension and are very stiff. So because we try to have just perfect linear behavior if possible. So you see the balls were also cone shaped. So just a few details. It looks a bit chunky in the end, I must say. But however, you have to keep in mind that these would actually be shoes on the proper structure. We didn't want to have something scaled or something smaller, but something that would actually be then used. So we further upgraded the whole system by injecting all the cracks, because we saw in the first test that we are actually getting some slip that we don't want to. And the problem is that because masonry is so fragile, it has so low deformation capacity, we try to avoid all the possible slipping. We rejected all the bottom seals, so we rejected all the little gaps that were between the shoes. We've slightly changed the bottom shoes just to see what happens if we use inclined screws. And if I move to a typical failure mechanism, so the masonry always failed with shear, typical shear cracks, and in the end it pretty much resulted in complete disintegration. The connection were failing at the bolts, which was expected because we've also slightly changed the shoes in the meanwhile. And so the results finally. This is the case for a glued-on cross-lamp wall panel. You can see that we actually achieved a 34% increase in resistance and about a 1/4 increase in displacement capacity. So the main difference from later tests with bolts is that we actually get a very high increase in stiffness already in the beginning, and the glue is actually working from the start. However, when the glue cracks, we're pretty much back to the same structure, or the unreinforced structure, but because we've accumulated a little less damage, we're actually getting some more displacement capacity after that. This was the first test of the bolted-on system, and you can see that the problem was, of course, because we had that little slip in the jointage, that we didn't really, the system didn't start to contribute as soon as we wanted it to. So we had to go to some, more serious displacements that the system actually grabbed hold. And what we finished up in the end was, okay, 0 increase in resistance. However, we got a 50% increase in deformation capacity. So the final system was this. We actually got quite a nice, almost a 40% increase in resistance, and we've doubled the deformation capacity. This was all pretty much due to sealing of the cracks, so we pretty much avoided all the slip that was there. Just, okay, I'm on red, just a few short words on the jointage. We also checked out the joints. So horizontal response of connections in masonry, the vertical response, the horizontal in concrete. We were also checking the variations if we're either bolting ourselves into concrete or masonry. And you can see that I've mentioned before that we try to achieve something like this. So the connection between the masonry and the steel plate would be pretty much linear. The connection between the steel shoe and the concrete, the crossline would be pretty much linear. And we would try to have, to have oral dissipation in our control in this joint connection right here. So just to sum things up, crossline panels do offer an interesting option for strengthening against seismic action. Attention must be paid to detail, especially when executing things. So gluing crossline 2RM is an option, however it's quite expensive and not very practical in the field. But the additional potential lies in the actual possibility of installing the panels on the inside of buildings, because that's where the actual vertical load from the floor can transfer after the URM walls subside, because there is quite some substantial vertical displacement in the walls. After the test, the walls are about 10 to 15 millimeters shorter, which means that all the vertical load goes on something else. It goes on crossline. If crossline is attached from the side, you have this sort of torsion, but if you put it under the walls, you can actually take the load of the floors onto crossline. So, thank you for attention. Questions?
Thanks for the presentation, very interesting. I have a couple of questions. One related to the retrofit with the masonry. You say that probably it's better to have it internally, but then you might have the issue to connect the wall to the slab. Because with these masonry buildings, if you don't have all the slab properly connected to the walls, you really have a very bad performance under earthquakes. Yeah. But the key thing is, so how do you then work out the foundation, the connection to the foundation, and how do you do the strengthening of the foundation? Because you increase 36% of the strength, means that you are going to have much more forces go to the foundation.
Of course, the problem is if we can access the initial or the primary foundation in the first place anyway, because otherwise we're pretty much forced to do additional foundation next to it. That's a possibility. If we're working from the inside, if we maybe have a concrete slab, or concrete foundation slab, that's a possibility, but it really depends from structure to structure, because when you're dealing with old structures, you never really know what you're going to get. Right? It's all full of questions. So, yes, of course, this may also lead to the necessity of new foundation. Absolutely.
So how do you do the connection of the wall to the slab?
There were a few variants. So in this case, we were actually attaching ourselves to the foundation directly. However, in the former ones, you can see that we actually attached ourselves to the wall at the top and at the bottom.
Sorry, I have to stop you so you can discuss after. Okay, so